Uh, just let me start sharing my screen. I hope you all can see it right now, my presentation.
Yeah,
Uh, as, as
it's
Paul
good.
said, I have the pleasure to be coordinator of project adOSSIG, which its full title is Developing an Infrastructure for Improvised and Harmonized Metrological Checks of Blood Pressure Measurements in Europe. This project is funded by European Partnership for Metrology and Innovations, and it is one of several projects that are focused on medical metrology. Here I would like to take a few moments to just introduce what problems are typical in medical metrology. If you look at it from the point of view of standard metrology, where we have physical artifacts and natural constant that define almost everything and that are the fundament of the traceability chain, the medical metrology is slightly more complicated. It's more often based on models or assumptions. The typical example is this blood pressure, which I will talk about a little bit later. Uh, Medical metrology also puts more emphasis on computational algorithms, and as a result, the traceability chain changes a little bit. There is usually no primary standard for these medical metrology quantities, but rather clinically tested devices or physiological signals that are in the end used for comparison with the devices in the field. And we cannot also forget the clinical trials that play a key role in accuracy statement of devices that are used within this part of metrology. As I mentioned, there are three projects that were funded within the Ampere. Two of them, the project Intense and Septon, were focused on intraocular pressure. The third one, the one that I'm coordinating and whose workshop we are having right now, is focused on blood pressure measurements. All these three projects have something in common, and that is the smart specialization concept that they are trying to develop and implement in certain fields of medical metrology. Just let me go briefly through objectives of these three projects. The first project, the oldest one, was the project Intense. It started in 2016, and it focused on intraocular pressure measurements, since these are crucial for glaucoma prevention. And as a typical for medical metrology, intraocular pressure measurements are usually taken as a mere supplement to classical metrology, and as a result, there are more and more problems with traceability of these devices. There were also no research capacities to provide traceabilities for new devices, and many European NMIs were lacking capacity and resources to build and to implement necessary parts. With this starting situation, the project was funded. Its objectives were quite simple: to build and develop research capabilities at CMI, thanks to knowledge transfer from German National Metrology Institute, PTB. Develop new development of new research capabilities, new measurements. Here I would like to mention an interesting output of colleagues from Slovakia who developed firstly virtual model of cornea and then physical transfer standard that was used within experimental interlaboratory comparison. And lastly, the creating of smart specialization concept. These three words, the smart specialization concept, will be mentioned quite a lot in our workshop. After a coffee break, Dana also will have a presentation on smart specialization concept, and how we do implement it in our project. And importantly here, this smart specialization concept was implemented in this field of intraocular pressure metrology, and also a strategic plan how to extend this smart specialization concept to other fields was drafted within Project Intense. Following in footsteps of Project Intense is Project Sefton. This extends the smart specialization concept geographically to Moldova, Northern Macedonia, and Bosnia and Herzegovina. And it's solely capacity building project. More or less it consists of training staff and interaction with the relevant stakeholders within these countries, with CMI acting as a key hub for this knowledge transfer. Recently, shortly there will be a workshop that will be held in Prague next week. A colleague of mine who's coordinating this project, Dominik Pražák, asked me to advertise it here, so I do that. If you would like to register or do you have any questions, comments, and so on about intraocular pressure measurements, please contact him at this mail. The third of these projects that is about to end in November is our project adOSSIG. As I mentioned, the long title is Developing an Infrastructure for Improvised and Harmonized Metrological Checks of Blood Pressure Measurements in Europe. Our motivation is quite simple. If we would want to accurately measure blood pressure, we need traceable devices. And why would we need to measure accurately blood pressure? The reason is quite simple. Hypertension affects a significant portion of European and world population, and it causes many problems thanks to usually symptomless symptomless sorry. As a typical example of medical metrology, blood pressure metrology has also the typical problems with many metrology institutes lacking the resources, capabilities, and knowledge to build their own infrastructure, or they usually take it as a mere appendix to classical metrology. Also, from regulatory point of view, there are problems taking into account accuracy of the devices. Sphygmomanometers that are used for blood pressure measurements can enter this field even if they systematically offset the measured blood pressure by 5 millimeters. And not to forget that there are very limited options how to test sphygmomanometers once they enter the market. With this in mind, objectives of our project were drafted, and we have 5 of them. They can be divided into 2 groups. The first one being technical objectives, which revolve about developing a new standard. We call it Advanced Oscillometric Signal Generator, which is a device that accurately reproduces real-life oscillometric signals that are then used in testing of the devices. And because this is a more or less new device, we also need testing procedures for this device, and to provide a traceability, uninterrupted calibration chain for our new standard. And as I mentioned, promised smart specialization concept finds its place also here. We are engaging with our original stakeholders, and we are expanding the smart specialization concept. Firstly, developed within the previous project Intense into new field, and we hope that after our project concludes, there will be a research capacity competence center and a working group that would persist beyond the project lifetime and that would provide knowledge transfer, support for devices in the field, and all interested parties even after our project is concluded. Going to first of our objectives, the development of the technical, to our technical objectives, to development of the advanced oscillometric signal generator, which is a keystone of our project. As I mentioned, this device should be used in the testing of devices. Its role in traceability of sphygmomanometers will be evaluated, and hopefully it will find its place as a supplement for clinical trials or in-depth testing of devices in the field. Going into the more details about the advanced oscillometric signal generator, as I mentioned, the keystones are database of oscillometric signals. Here is a schema how it all works. Oscillometric signals are small pressure oscillations of low amplitude, usually between 4 and 10% of cuff pressure. And these are recorded by the recording unit and stored in a computer and further used in the simulator or in our advanced oscillometric signal generator. Our project uses a vast database of oscillometric signals that were previously collected by Newcastle University about 20 years ago. The vast database contains about 1,300 signals from approximately 600 patients, and this is an important part of our simulator. Within this, it would be only hardware, which consists of relatively few parts. The most important is the mechanism that generates these oscillometric signals to tested devices. It consists of 3 pieces: lever and pressure chamber connected with a motor, and the pressure generation is done by the tested device. After colleagues from PTB developed this device, they performed testing of stability and applicability of the simulator. The testing procedure was based on a technical specification ISO 81060-5 with 2 parameters evaluated. The first one was the repeatability of oscillation pulses, and the second, the repeatability of the shape of the simulated oscillations. With both parameters tested, the results were very good. Here we can see a standard. Here we can see, and on the left side, 10 repeated measurements, 10 repeated pulses, and how they agree with each other. On the lower portion of the presentation, there is an average compared to reference the simulated signal. On the right side, then the standard deviations and squared correlation coefficients, which are close to 0.99. Which and all these parameters more or less fulfill the requirements from this technical specification that was mentioned previously. So our simulator works very well, and as I mentioned, the project is not only about capacity building. Sorry, it's not only about technical development, but also about capacity building, which will be later presented by Dana Rosu. I hope that for introduction, this would be sufficient. If you do have any questions or comments, don't hesitate to ask. If there are no questions and comments, I would immediately continue with the second part of this presentation, which would be the results of our testing of several sphygmomanometers and the results that we obtained. So, since I don't hear any question, comments, and so on, so let me continue. In 2020, last year in 2021, after the sphygmomanometers, after the advanced oscillometric signal generator was already developed within our project, and at the time it was being tested at University of Ljubljana. We were contacted by local newspaper Mladá fronta Dnes, who wanted to perform some consumer test of sphygmomanometers. They were hoping that it would be quite it would be non-problematic testing with 12 sphygmomanometers, all utilizing oscillometric method and let's say within a lower pressure range. Their idea was that it would be something quite simple, something like calibrating a pressure gauge, which after some discussion and explanation to them, it could be done theoretically in 3 simple steps. Simply connecting the device to a standard of greater accuracy, testing in desired number of pressure points, and then evaluation of results and determining the uncertainty budget. However, when it comes to sphygmomanometers, this procedure is hard to adapt, and if we would do it, we would only test the ability of the devices to display the tested pressure correctly, which for blood pressure measurements is unfortunately insufficient, since the measured pressure and static meaning means completely different quantity from the measured value. It's from the measured blood pressure value. So after these explanations and discussion with the newspaper representative, we pointed out that there are 2 options. The first one was to include some test protocols for sphygmomanometer evaluation, which consist of clinical trials which require vast number of test subjects whose the blood pressure is measured by some doctors with reference measurement and then with the tested devices. Or there was another option. Sorry, I skipped the slide. There was another option to use our advanced oscillometric signal generator that was developed and used within the project adOSSIG. They simply agreed, thanks to time and costs for the use of the oscillometric signal generator. We agreed on use of our developed procedure for testing the sphygmomanometers, and sorry about that. Yeah, we agreed on a use of the developed procedure that we developed within the project adOSSIG. The procedure is based on this European standard 81060-2, clinical investigation of automated sphygmomanometers. The procedure is based on quite simple assumptions that if we test the sphygmomanometer with a large enough sample of 85 test subjects divided according to age, sex, blood pressure values, without any significant obstacles for blood pressure measurements, with several repeated measurements, then that we could obtain some quantitative and qualitative description of the testnet devices. As I mentioned, this device that we used was the device that we used for testing was our advanced oscillometric signal generator, which utilizes vast database of oscillometric signals, oscillometric signals with courtesy of Newcastle University. And these were used for the testing. Once again, how device is constructed, what are its key components, and how we tested. Our test procedure consisted of of two stages. The first one consisted of 85 repeated measurements representing 85 test subjects, and in the second stage, which was to test the repeatability of measurements with selected signals. We selected 85 signals from the Newcastle database. These represented 42 men and 43 men and 42 women with various blood pressure values, with age of these test subjects spanning from 16 to 82 years of age, average of 52. The blood pressure values used were from wide range of systolic pressures between systolic blood pressure between 80 and 208, diastolic blood pressure varying between 40 and 132, and the difference between those two values was in average 56 millimeters of mercury, with a difference spanning between 19 and 126 millimeters of mercury. On the right side, you can see the distribution of blood pressures we tested the devices with, and all these parameters fulfill the requirements that are that were used. These requirements from this European standard 81060-2. The measuring setup was something like this. Each device was tested with its original CAF connected to simulator or the ILSG by TPs. And prior each testing, we adjusted the simulator for we adjusted and calibrated the device with each CAF, so we would minimize the internal volume influences. Going to devices that we tested, as I mentioned, there were 12 devices. Unfortunately, one of these proved to be defective from the very beginning, and it was not included later in the testing. Other than that, there were 11 devices remaining. In total, 12 tests were performed because one of the devices, Brown exactly, was equipped with 2 different CAFs. By looking at the manufacturers, you can see that several of the devices are more obviously manufactured by one manufacturer, all of them produced in Southeast China. Some of these devices measured or determined the blood pressure by only increasing the pressure in the cuff, while 5 of these measured also the blood pressure during the pressure relief. By looking at the site doubleeducational.org, there also can be found some clinical, already performed clinical trials on these devices. However, all of these that were found were done with other than this European standard test protocol. These were done with European Hypertension Society protocol version 2010, with the main difference being a lower number of test subjects included. This test protocol includes only 33 test subjects, while the European standard requires 85. As I mentioned, we tested devices with 85 signals, all of them, and the results were calculated average error and the standard deviation. The European standard says that in order to pass the clinical trial, the device should perform with average error of 5 millimeters of mercury, plus minus 5 millimeters of mercury, or lower, and standard deviation of 8 millimeters of mercury or lower. As you can see from these results, on the first stage, only 4 devices performed within these requirements. However, most devices did not deviate so much with, I would say, 2 examples of large cuff used with this Brown's large exact fit and sphygmomanometer called marketed as Esperanza, which proved during the testing as more somehow defective. If we display the test results a little bit differently in graphical form, we can see that a lot of results are within an acceptable region of, I would say, plus minus 10 millimeters of mercury. These are all results divided by systolic and diastolic blood pressures and respective indication of the tested devices. We can say that a lot of devices performed quite well within certain blood pressure ranges. However, there were certain blood pressures where all devices produced faulty results. These faulty results were used in our second stage, which I will get to in a minute. Just briefly, let me show you the results divided by, let's say, normal blood pressure, acceptable range, anything below 140 millimeters of mercury of systolic pressure and diastolic pressure of 90 millimeters of mercury. These are the thresholds that the European Hypertension Society considers the hypertension. So we can see that a lot of results were within acceptable region of of plus minus 10 millimeters of mercury. However, with some notable exceptions that which exceeded these limits. And interestingly, these were a bit more or less consistent over the tested devices. If we look at the other field, or other half of the blood pressure range, we can see that in hypertension region, there are devices that perform well, yet there are more signals that are outside the region of this plus minus 10 millimeters of mercury. And most critical situation seems to be that the devices seem to underestimate the blood pressure, which could have, if used in a clinical setup, dire consequences. If we combine more signals with a region that it's not with combined with or and but with or, then we can get a better view on the tested results. As I mentioned, there was also stage 2 of our this testing. This stage 2 consisted of 3 signals that were used in the first stage. The first one of these signals was representing normal blood pressure measurements, 126 millimeters over 84 millimeters of mercury, and this signal was used as a representative, as I mentioned, for normal blood pressure measurements, with the goal to evaluate the repeatability of 10 repeated measurements for each of the devices. Then 2 more signals were used, both representing somehow hypertensive patient. The first one, 177 millimeters of over 100 millimeters of mercury. This one was selected because it had the highest average deviation of systolic blood pressure, across all devices in the first stage, and the second signal selected 183 millimeters over 132 was selected due to highest average deviation of diastolic blood pressure measurements in the first stage. 10 repeated measurements were performed with each device, and each of these signals, again, after adjustment and calibrations, and you know, are the signals in the scope of the testing. And here are the results. They are divided by systolic and diastolic blood pressure reading. You can see that the average for the later two, these hypertensive readings, these signals proved for all devices to be extremely faulty, with deviations in the region of almost 30 millimeters, on average, almost 30 millimeters of mercury in systolic or diastolic. Yet what was quite surprising for this second stage of testing is that the devices provided these results systematically with, I would say, acceptable repeatability. The standard deviation hardly exceeded the standard deviation never exceeded 3 millimeters of mercury within this second stage. Most results stayed within very reasonable 2 millimeters of mercury. This testing proved that the devices, although they could be faulty, they can provide under some ideal conditions consistent results. So even if some person whose blood pressure is measured with one of these devices has a heart condition or hypertension or any condition that needs to be monitored, if the devices are used properly, then the results could be significant, could be of large significance, and if tested, if everything done right, trends monitoring could be possible. Yet this asterisk with monitoring of blood pressure trends requires the blood pressure measurements to be performed with all recommendations for correct blood pressure measurements to be taken into account. So, for example, a relaxed manner prior the measurement. So, remove not to use any or to minimize any influencing factors prior the blood pressure measurements, like excessive activity, excessive intakes of liquids, caffeinated drinks, smoking, and so on. And as I said, the conclusion of this second stage testing was that the devices could be used for this blood pressure monitoring, however, with precaution taken into account. Of course, further testing of this sphygmomanometer testing is necessary, since within this testing we only tested devices of I would say lower price range, as I mentioned, because the price of these devices was between 15 and approximately 100 euros. I dare to say that if we test devices that are intended to use in clinical environments, which are of course much more expensive, the results could be significantly different. Yet also a question that remains open is that if we would use different signals from the vast database that there is available, how different the signals would be. That is also a question to be answered by future testing. The first, the most important parts that this testing answered is that the sphygmomanometer evaluation using this simulator could be done within a reasonable time span and hence reasonable cost, which could be a great help in a clinical environment or any future testing with for example, problematic blood pressure ranges, problematic setups, and so on. And we also, thanks to this, confirmed that our developed simulator could be used in in-depth testing of sphygmomanometers. This concludes my presentation. If you do have any questions or comments, don't hesitate to ask. I'm happy to answer them. Yeah, I'm happy to answer them.
Thank you, Václav, for your two very good presentations. Some really interesting data on that second one regarding the testing. Oisin, I'm not sure if we can take any questions at this point in time, or if they'll come at the end of the session later on.
Yeah, Paul, we can take questions. If anyone does have any questions, they can just pop them into the Q&A. You'll see that down the bottom. So if you have any questions, you can pop it into the Q&A. Or as Paul said, we can have a chat. You can bring them up in the discussion later. So whatever suits you guys. So the Q&A is the function for the questions throughout.
Václav, I have one question, I suppose. All the devices that you tested, were they all were the cuffs that are used on the upper arm? Is that correct?
Yes, that is correct. All the devices were used were upper arm cuff. We or the newspaper, after some consultation, excluded any wrists or wrist devices or smartwatches and so on, although they are on the market within the setup that we have. The upper arm cuff was the device that we were confident with, and we expected no significant problems in testing these.
Because I have seen ones for sale now that I think have the cuff on the wrist. I'm just wondering, you don't have any view or any, we haven't tested any of those, or we don't have any comparison regarding how good they are compared to the other ones. I have my doubts.
Yeah, exactly. These devices, I would say that they are more prone to measurement errors coming from position of these devices. The cuff device, the upper arm cuff device, is placed more or less, if not measured totally wrong, in level of your heart, where the wrist cuff device might be placed incorrectly. So there can be unwanted yet significant deviation, and the results might be biased by this. So we excluded all of these devices.
And if I may add, we did test some of the wrist devices, which this can also be done using the simulator. You just have to unplug the cuff a bit more with a bit more power off, but then you can still use a T piece and put the simulator's input between the small cuff around the wrist and the device itself. And there are a couple of devices which were clinically validated and really successfully. I don't remember now, but I know that Omron had one of those. So basically, even using this type of simulator, it could be done. I mean, we did try it, but I have never tested really like thoroughly like Václav did. So, but it's possible.
Okay, I don't see any questions in the chat area yet, so maybe we'll look at some for later on. So again, thank you, Václav, for your two presentations. We're slightly ahead of schedule, so it might be a logical time just for a quick break. We said we'd have so I think we'll take maybe if we take a 15-minute break, we can start back with Gregor, let's say in 15 minutes, if that suits. Are you okay with that, Gregor? Yeah. Okay, I think we are probably ready to start back again. again, to those that have recently joined, maybe missed weren't there at the start, again, welcome to this this webinar on the adOSSIG project, and just which is, I suppose we're coming to an end on the project, but this is to update people and update stakeholders on what has been done during the course of the project, and to open up an opportunity towards the end of this session to, I suppose, ask any questions, and to particularly in relation to the whole concept of smart specialization, which we will be discussing later on. So I think we'll move on. So our next speaker is Dr. Gregor Gersak. He's professor of the Faculty of Electrical University at the Faculty of Electrical Engineering at the University of Ljubljana in Slovenia. And Gregor has spent a lot of his time in this project on looking at the, I suppose, calibration procedures, traceability, and uncertainty budgets in relation to using the advanced oscillometric signal generator for testing of blood pressure devices. So, Gregor, I'll hand over to you. Thank you.
Thank you. Thank you, Paul. So basically what Václav was showing us before was how to use a simulator to test blood pressure monitors, and our work was based on how to test the simulator, so to test the test device. Let me just share my slides. Like I say, so basically we were interested in the way a simulator could be calibrated. Yeah. So the starting point, or the promises, or some envisioned ideas we had at the beginning, was that the simulator should be accurate enough, should be reliable enough, robust enough to be suitable for testing blood pressure monitors. So what does this actually mean? So, and we decided on, I mean, from experience really, on some target uncertainties written here above. So basically, we said the simulator, if we want it to regard it as a reliable testing device, should have uncertainties in the order of a millimeter of mercury, around a millimeter of mercury, and it will be a bit easier to explain how the testing of the simulator was done if I explain firstly how the simulator works really. Basically, this is a pressure pulses device which generates pressure pulses like this here, written shown here, and these pulses are not like huge. They're a couple of millimeters of mercury is the amplitude, like from -10 to 10, and the shape looks sort of sinusoidal somehow, and this is the output of the simulator. And it might be easier if I show you a video how this is done. So basically, this is a device under test. So like a really low cost blood pressure monitor. And I mean really low cost, because we also did a couple of tests using these devices, which are using this test piece, T-piece here, are connected to its original cuff. This is this black rubber hose here, and this tubing here goes to the simulator, and this box here is the simulator. Here on the monitor, you will be able to see the signals which simulator produces. So this is the output of the simulator. So let's run this. This device starts to pump the pressure. Okay, now it's deflating really. And while, according to this pressure here, the simulator generates pressure pulses. Because it's deflating, these pressure pulses will be smaller and smaller and smaller. So this is a device which measures, like Vasa said, which measures on the way down. Okay, now it pumped the pressure up, and then it slowly decreases the pressure, and depending on the, so this is what the device itself does. It pumps up the pressure above the systolic one, and then it stops, and then it deflates the pressure down. And during this deflative phase here, the simulator starts adding these pulses. So these are the pulses added by the simulator. Basically, the base curve is produced by the blood pressure monitor, and these pressure pulses are produced by, or generated by the simulator. And we were interested in how repeatable and how reliable these pressure pulses are. This is another picture of deflating pressure with all these pressure pulses, and I put some pictures of the pressure pulses here. So basically, the simulator generates the proper pulses according to the pressure, meaning the amplitude of the generated pressure pulses depends on the pressure in the cuff. And firstly, the pressure pulse is small, as you can see here, like small pressure pulses amplitude, and then they get larger, and then they get smaller again. And if I put all this together into one picture, this is how this looks like. So the red curve here is what the simulator is producing. So this is the output of the simulator. So basically, when the cuff pressure goes up and then deflates, at a certain point, these pressure pulses start to grow. And the largest would be the highest pressure pulses are here, which corresponds to these higher peaks here. And then later on, the pressure pulses go down, and then the device completely deflates and the pressure pulses are gone. What you can see from this picture is that the simulator actually produces the pressure pulses twice, once here and once here. The difference is that this part here is slowly controlled deflation of the device, which means that a lot of pressure pulses, which basically correspond to the heartbeats, would happen. So there are a lot of pressure pulses here because this deflation is slow. But there are also pressure pulses on the way up, meaning also on this flank here, when the pressure is increased, there are also pressure pulses here. Just they're not that many because this happens fast, and the simulator doesn't have a lot of time to generate the pressure pulses. But basically, this pressure pulse here corresponds to this pressure pulse here. Just it's done fast, in a fast way. And by the way, this is mainly also the difference between the devices which measure blood pressure on the way up, when they just pump the pressure up. They're using these pressure pulses, and classical devices you measure blood pressure when deflating. This means that they're using this side of pressure pulses. And the algorithm, the mathematical algorithms in these devices just put some envelope on these pressure pulses and then calculate the systolic and diastolic pressure from it. Why am I showing you this? Because what we did when testing simulators, we were interested in repeatability of such pulses. So how, if the simulator is electromechanical device, it should be repeatable, robustly repeatable, and this is what we tested. So basically, the calibration of a simulator, of any simulator, not only the physiological simulator, which is the result of this project, of adOSSIG project, but also of any other kind of simulators, because there are also commercial simulators available. So basically, we divided the calibration in two parts. One part is the static calibration. And the static calibration just means that we would be testing the simulator's pressure gauge, pressure transducer. This is done in a classical way, like with all manometers, with all pressure measuring devices. We would plug the simulator to a residual volume, to a metal box with different volumes. Then, and this line here is the tubing. So the pressure generated by the simulator would go into the volume here, into the pressure generator, and into the reference manometer. One important part is the pressure generator, either like manual one, like this rubber ball, or like electronically controlled device, like a calibrator of some sort, or any sort of pressure generator. And then what we need is a reference pressure transducer, accurate enough for all this. So basically what we did in static calibration, we were calibrating in a classical way the pressure transducer of the simulator. And this is the front panel of the simulator. Here the operator can see, can set the desired systolic and diastolic pressure, can see what are the all different medical background of the person whose physiological signals were stored into this device, and also some controlling features and so on. And one of the things which is encircled here is the pressure. So this is basically the pressure in the tubing or in the cuff. And in static calibration, we are planning to statically calibrate this device. And this is usually done, it can be done in different ways. And this is like so-called the comprehensive method of calibrating devices, meaning that you use 11 steps of pressure from low in the whole measuring range. So if the blood pressure monitor measuring range is from 0 to 300 or 350 millimeters of mercury, we would divide this from 0 to 300 millimeters of mercury to 11 stages, and then measure the pressures in all these 11 points. So here on the y-axis is pressure, on x-axis is time. So we are measuring the errors in 11 points here, and then 11 points here, and again 11 points here, and up and down. And we are using these 3 series because using the 3 series, we can also calculate errors because of the hysteresis of the device. We can calculate the repeatability of the device and stuff like this. The uncertainties, or the uncertainty budget, meaning the detective work, what are all the quantities which can influence such a static calibration, are written here. There are also others, right? Of course, but the major ones are written here. So like the uncertainty of the reference instrument, the repeatability of both the simulator and the referent manometers, and then some errors which come from the pressure generators, from all the tubing, the leakage, also some environmental conditions like temperature dependence, also humidity dependence, and so on. And this is really nothing new. Here are some typical uncertainties. These are the numbers. So this is something which like every pressure lab is capable of doing it of doing. So basically what we did in this part, in the static calibration part, we calibrated statically the pressure transducer of the simulator. But the interesting part was, of course, the dynamic calibration. Dynamic calibration means that now we are testing the outputs, so these waveforms of the simulator. Or to put it even more simple, simulator is a generator which generates pressure pulses. And now we would like to evaluate and somehow calibrate these pressure pulses. Dynamic calibrations are, in the world of national meteorology institutes, are quite seldom because they are quite complex. And this is one of the so this part, the dynamic evaluation of the simulator, was much more complex and challenging than the static ones. And these are the results. So basically what we did is the dynamic calibration was divided, as Vasav already mentioned in the previous talk, into two huge categories. One is we would evaluate how robust or how repeatable the amplitudes of these pulses are. This is now the front panel of one of the instruments when we were testing the simulator. So simulator was basically set, so it was plugged to 96 millimeters of mercury static pressure, meaning that according to the 96 millimeters of mercury, the simulator would pick a certain physiological signal and then use the shape and the form and the amplitude of these pressure pulses according to this 96 millimeters of mercury. So if we expose the simulator to a static 96 millimeters of mercury, it would just output reproducible. They should be reproducible, repeatable pressure pulses, which should be exactly the same. Like if the simulator would be an ideal device, these pressure pulses here would be completely the same. Like every single one of them would be equal to the previous one. And what we did afterwards, we were testing the amplitude of these pulses, which ideally should be all the same. So the difference in them should be like 0 millimeters of mercury, which of course is not the case. Simulator is by definition an electromechanical device which has some problems, or it cannot be absolutely accurate. And it also ages, and the materials get are tiring and so on. So the time drift is expected. Another thing which we did from out of such a test was also evaluating the pulse shape. And pulse shape is shown here. And the pulse shape, meaning one such pulse, was done in such a way that we were segment this pressure pulses waveform, and then compare different shapes. So to put it more simple, if you want to dynamically calibrate the simulator, at least 4 stages should be taken, should be done. First part would be amplitude stability error. So we would make the simulator output same signals, and then we would just evaluate how the amplitude, the maximum amplitude, would change. Ideally, they would not change. The second one was cutting these pressure pulses into single pressure pulse, and then comparing the shapes, and we could by putting all the pressure pulses together, we could see how the pressure pulse shape changes. Ideally, it should not change. All the pressure pulses should be the same. And then we did some, and there are some tests concerning the cuff volume, because cuffs are different and cuff volumes can differ, and then we can expect that there are differences because of the transfer function in the device itself, some differences in how the simulator works. And of course, all these devices should be, I mean, simulators should be able to work, to function reliable in some in logical, like environmental conditions, like from 10 to 40 degrees centigrade, and like normal normal humidity. So firstly, if I start with the shape and amplitude, we decided on a criteria which would say that we need to have 10 consecutive pressure pulses, and then we just statistically analyze how the amplitude is stable, the stability of the amplitude. And again, with the pressure shapes, we also envisaged 10 consecutive pressure pulses, and then compare the forms of the shapes of the pressure pulses. What we did, we were also using some like standardized physiological parameter shapes, physiological signals, which came from this huge physiological database, which was collected in UK, and we helped. We based all of this to this ISO standard, this technical specification, where there are a couple of static pressures already suggested as the static pressures where the simulators should be tested. And what we did, we used these same suggested numbers and found the right physiological signals, or if you want, the right people in the database having like 120/80 millimeters of mercury with pulse rate of around 60. And we did find people who approximately matched these numbers. And then we did all these pulse shape and amplitude stability tests using these physiological signals. This is one of the pictures how the segmentation would look like. The red line here is the output of the simulator, and these dark and light blues are how the pressure pulses are segmented. And then the maximum or minimums of each individual segment would be statistically compared. The cuff volume, why actually the cuff volume? The cuff, you have to have in mind that all the blood pressure monitors, they usually, the home devices come with one cuff, sometimes two. But usually these devices can, a lot of different sizes of the cuffs could be connected to the blood pressure monitors. And here, like this orange one is for neonates, for really small kids, and then larger and larger adults. And the thing is, usually, sometimes the monitors themselves are tested clinically using more devices, because you have to have in mind, if you have a single cuff which has its own volume, and then the tubing, a device having a small cuff and the same device having larger cuffs, this could be regarded as two different devices. So because of the whole volume transfer function, then the pressure transfers from the arm or wrist transfers differently to the pressure sensor in the device. So cuff volume is an issue, and we all know that it's important, and also the length of tubings can sometimes be important. But the thing is, if we test the simulator should be able to test blood pressure monitors, no matter how their cuff volumes are. I mean, in some like common sense range. So we decided that it should all the tests should be performed using 100 millimeters and 500 millimeters volume containers. These are these boxes here. Why? Because 500 is like the classical normal adult cuff, and this is neonate's normal adult cuff volume approximately. And we did we envisaged some requirements, like how the pressure passes and should be tested, the amplitude and shapes to be tested using these two containers, and the differences should not exceed 0.01 millimeters of error. So we did a lot of testing. We decided on a number. Now currently we are testing also commercial simulators, not to recommend too strict numbers, too strict requirements for the simulators. The last test would be an environmental dependency. This is usually done, I mean, this is done in climatic chambers. Climatic chambers are boxes where you can control temperature and humidity. Temperature usually from like -50 to 200, and the humidity from 0 to almost 100, non-condensing. Anyway, we decided, also based on some technical specifications and some ISO standards and OEML. This is legal metrology organization, which also has some recommendations also for blood pressure monitors. And this is like classical range where simulator should function properly in around room temperature from 15 to 25 degrees and from 15 to 85% relative humidity, non-condensing, of course. So we decided on that these conditions should be tested in the least in the most challenging environment, meaning from 15 degrees and 15% and 25 degrees centigrade and 85 relative humidity. So with outer limits, and the differences should not be larger than 0.5 millimeters of mercury. All this stuff is basically, all these tests are put together. Why? To test the simulator, that it's in metrological sense good enough to test blood pressure monitors. And we've come to some conclusions which are written here. But typically, like typical uncertainties would be something like this. So the combined standard uncertainty, like really ideally, should be in the order around 0.1 millimeters of mercury. So if we put all of this together, like the static accuracy and dynamic accuracy of a test simulator, and we would come across some numbers like this, we would reach 1 millimeter of mercury. This is this number here. We would reach it for a simulator. Of course, this number is it depends on the simulator, it depends on the way it's done, and so on. So currently what we are doing now is we are testing this procedure using a commercial simulator, which inherently should be a bit less accurate, but still the number. I mean, if we expect the uncertainty of a commercial calibrator simulator should be a couple of millimeters of mercury should be the value. So, and to conclude, really, what we did, we were using some test signals. These numbers here are physiological signals of living people who had their blood pressure recorded. This is the person number 380, which had 120/80 blood pressure, and this person 562 was hypotensive, and so on. So test signals were used, and we did tests like leakage test, cuff volume test. We did not only 100 and 500, but also other volumes. We tested the shapes really, and we were also using some features of the simulator, and these features of the simulator are like on here is a part of front panel of the simulator, and there are you can also play a bit with the simulator amplitude, meaning that some devices need larger amplitudes, and that's why these amplitudes can also be amplified, and that's it. So in short, what I presented was that in order to test simulators, the testing devices, we did it in two ways, statically and dynamically, and that's it. Thank you.
Thank you, Gregor, for a very comprehensive overview of the testing and the that was being carried out. And as you say, I think certainly dynamic testing is challenging to metrologists. It has a lot more variables that we have to worry about. Like I say, I think if anybody has any questions to Gregor's talk, you can put it for the moment in the chat, or we can hold for later on when we will have an open panel discussion. Just before and your peers, Gregor, the physiological samples that were used, can you recall how many samples are in that database? You can unmute.
I can maybe answer the question if Gregor cannot.
Yes.
So the database contains a little bit over 1,000 signals from over 600 patients.
Okay, thanks, Diana. There's a question there from the chat. What kind of dependency on humidity can we expect in the pressure measurements?
What we noticed by now is that the humidity actually more or less influences the material of cuff, and this rubber bladder which is in the cuff probably depends on the material of the cuff. I'm not quite sure what, but it's all pretty much negligible. So we do this is like a test which basically is every quality made simulator would pass it easily, but
okay.
if you have like some which might be which would work on other, because usually the simulators don't actually all work on the same principle as this simulator works here. Sometimes they use voice coils or some other electromechanical way, or some other ways which look like more mechanical, and then humidity can influence it. But like I said, what we did, we never saw nothing dramatical, really.
Okay. Okay.
Sorry, Paul, I just have a question here. Just in the someone's raised their hand. I think it's Stefan. So I'm just going to allow him to speak. Potentially, I think he has a question. So
Yeah, sure.
I think you just have to unmute. There you go. So
Yeah,
far away.
I hope you can hear me. This is Stefan speaking from formerly PTB. I just wanted to add the information for you that Alan Murray from Newcastle, I don't know if he's also present today, and myself, we have investigated in depth how the shape of the oscillations is generated by the simulator and compared this with the reference values from the database. We did this on 7 selected pulses because they cover the range, the normal range for the blood pressure measurement. And we found that is, I think, extremely good correlation between both. We are just preparing a paper on that, showing the potential of the simulator. And maybe just one additional information in ISO 81060-5, which Gregor also mentioned several times, there is a comparison between the average of the 10 repeated pulses and each pulse, and the R square has to stay within 0.998, which is really a very challenging requirement. And we found that for these 7 pulses which we analyzed, this is fulfilled. Compared to the reference, the results are not that good. They are still for R, the mean value is 0.994, but it is comparing not with reference, but the mean value is easier to fulfill. But still, it is, I think, an excellent value. And Alan and I hope to publish these data in the near future. Thank you very much.
Thank you, Stefan, for that update. I think I have a question from the chat. For Gregor, what type of digitizer was used to acquire the dynamic pressure waveforms, and was this a limitation on the measurement?
Yeah, of course. Yeah, this is precisely what's hidden in something I said in the beginning. Not a lot of labs, metrology labs, would do the dynamic measurement because it's the dynamics is completely other field, really. And of course, the acquisition of the pressure signal is very much dependent of fast pressure signals is very much dependent on the pressure transducer and all the digital to analog parts afterwards. And what we used was a really good. We didn't know when we purchased it, we didn't know that it's so good, but we used it. It was a really good pressure transducer produced by General Electric or Druk, really. And it's a classical unique 4000 device, but they do have some premium version of it, so it's really accurate. Like and this is of course in statical sense, but we did a lot of testing using fast signals, and please bear in mind that blood pressure pulses, these are not like considered something really fast, because they happen like once. The frequency of the pulses would be 1 hertz if someone would have 60 beats per minute blood pressure. So it's not really fast. So concerning the electronics or the acquisition device, it's not so difficult. What we did in parallel, I was not talking about it, but in parallel, because we are also a part of our lab is also acoustic lab, And these people, the acoustic people, they work with fast signals. And what we did, we used some kind of a special microphones, which were then added in parallel to this pressure transducer, so we could double check how the dynamics would change the measuring results. So, but to answer this, what type of digitizer it was used? It was a really really good pressure transducer, and nothing really special. Not a lot of conditioning of the signal, really. Some of it done digitally.
Okay, thanks, Gregor. I think Dana, you have a hand raised.
Yeah, I have a very fast question. You mentioned that you tested the simulator using also affordable devices and also devices intended for professional use. What was the difference that you noticed, or was there a significant difference, or did you notice significant issues during the testing?
No, actually, we didn't test any of the like ER devices, like the clinical devices. So I have no experience with those. What we did is we like intentionally bought a couple of pressure monitors which are low cost. Like I can tell you all about the low cost devices, the ones that you can buy for €7. But I have no idea how is it with patient monitors and the inbuilt, the embedded devices. Like,
did you also test let's say an expensive Omron device, or?
Oh yeah, we did.
Okay.
Yeah.
And did you notice significant differences?
They're much more reliable, repeatable. This is the basic difference, and the quite similar as Václav said when he was talking about the comparison they did. They were just much more reliable. And these devices, which were not that bad, really, the low-cost devices, they were some of them had like the quite well below the threshold errors. But what I did really notice is that usually the low-cost devices really work great for healthy people, meaning that if they would be plugged into a simulator generating blood pressures, like normal blood pressures, like normal tensor, like 120 or 80 or plus minus 10, they work great, even though they cost like €10, really. But as soon as you get some more complex shapes of the pressure pulses, or arrhythmias are nightmare for those devices. So if you don't have like very strict heart rate, the constant heart rate all along, then they would have problems. And what I also noticed that we also did some tests in climatic chambers, and if the temperatures are too high, not low, but too high, the errors will also drastically increase. So to put it more simple, they're just not reliable enough. But I think this is like in all measuring devices. If you have a low-cost one, it might have not large uncertainty, but in the long term, if you calculate also like time drifts and so on, I think they're not that good. So these were our experiences.
Okay, thank you.
Okay, thank you, Gregor, for that and for your presentation. We'll move on to our next presentation, which is covering the area of smart specialization, the smart specialization concept, I guess, in the area of metrology for blood pressure measurement. And this will be presented by Dana Rosu. Dana is the medical device coordinator for the PTB and is a partner to this in this adOSSIG project. So Dana, I'll hand over to you. Thank you.
Thank you, Paul. So please let me know if you see the presentation.
Yeah, it's good. We can see it.
Great. So as Paul said, I will talk today about smart specialization concept in metrology for blood pressure measurements. If I were to summarize our project in two main scopes, one would be the improvement of the reliability and accuracy of blood pressure measurement by developing an advanced oscillometric signal generator for the verification of automatic swing manometers and of procedures for the periodic recalibration of this type of devices. And the second one would be the development and implementation of a smart specialization concept for the field of blood pressure metrology. While the first scope was discussed at length during the previous presentations, I will concentrate on the second one, which is developing and implementing a smart specialization concept. Now, what is a smart specialization concept? In general, the concept concentrates on the definition of a limited set of priority areas for public investment at a region or national level. This type of concept does not impose the same set of priorities and requirements for large regions, like for instance, Europe or all countries in the EU region, but it nominates activities at regional level that aim to explore and discover new technological and market opportunities that could be beneficial for the economic and social development of certain region. The main reason for implementing such concepts are the persistent gap on one side between European regions with respect to research and innovation access, as well as political structures and interests, along with the very well-known financial restrictions. Now, let's discuss this concept on the particular case of blood pressure metrology. What are the reasons for needing such a concept in this field? The main ones are the lack of harmonization at the European level, considering the metrological requirements specifically, while the new EU legislation works towards the harmonization of requirements for medical devices when entering the market, no specific metrological requirements exist, leaving each country to develop its own requirements. This leads to a very heterogeneous situation in the field of blood pressure metrology, with some of the countries completely ignoring the field, while others independently developing their own metrological requirements. The situation is not only confusing and flawed for metrology experts, particularly for emerging NMIs, which suffer from not having a clear goal when developing their structures, but particularly for manufacturers that have to comply with different regulations in different countries. Other two important points to mention here are an insufficient metrology infrastructure at NMI level and a lack of resources and know-how at NMI and regional level. These 2 points are often connected, and the main reason for it is that blood pressure measurements require expertise not only in the field of metrology, but also a lot of medical expertise. This is rarely acknowledged, and in practice, the field of blood pressure metrology is often created as an appendix to pressure metrology. As a result, instead of establishing highly needed true traceability for modern dynamic oscillometric instruments, only static pressure measurements is verified. And I think Gregor discussed quite at length in his presentation about this point. One cannot forget here the last point, which is in some cases the lack of interest of certain regions or NMIs to invest in the further development of the vast field of blood pressure metrology. This can be, but is not always correlated with a lack of resources, but rather with political, technological, or scientific priorities of certain regions or of certain NMIs. The main scope of the smart specialization concept proposed is to ensure the access of all European NMIs and their customers to high quality services in the field of blood pressure metrology. To achieve this, the concept has to establish a foundation for long-term partnership beyond the end of this project in dynamic blood pressure metrology. The smart specialization concept will allow the involvement of NMIs and DIs to optimally utilize their limited national capacities in a smart division of labor and resources. Now, how do we achieve that? Well, there are three main points that we engaged in. First, the creation of a network in the field of blood pressure metrology and expanding this network both geographically and technologically to different medical devices. And secondly, and maybe most important of all, creating a competence center for advanced blood pressure metrology. As a third point, we have narrowing the gap between the capabilities of different regions in Europe. I will go now point by point and discuss them a little bit more in detail. The project started with a relatively small network of European NMIs and DIs, which were also the proposers of this project. The network contained 9 European countries that are shown on this map, with various expertise in the field of blood pressure metrology and with very different political backgrounds. The network was expanded during our project to other countries in and outside Europe. Our network comprises at the moment experts and institutions from 15 countries and from different fields. Besides metrological experts with which we started, we have medical experts, regulators, academia representatives, and certification experts. Their input is very valuable to us, as it is not only used for our technical developments, but also to consolidate the smart specialization concept and as a consequence to ensure a coordinated and optimized approach towards a European network for blood pressure metrology. As future plans, we have to expand the network to other regions, not only restricted to European region, also stakeholders and technologies, and very important for us and our goals to ensure the persistence of the network before the end of the project. In expanding the network, we intend to concentrate on establishing a contact, particularly with legislators and manufacturers, which are currently underrepresented in our network. Equally important is creating a long-term partnership with other networks and projects in the field of medical metrology, as our final scope is to create an extensive medical device metrology network. Another important task is to ensure the persistence of the network before the end of the project. And I mentioned this several times. Besides the network that we created and we expand, and we will continue to expand, we created a working group on advanced blood pressure metrology. This working group was established last year and met twice until now. If the network comprises a wide variety of stakeholders, the working group will be comprised mainly of metrology experts. These experts will form the core of the working group. Temporary members can join the group depending on their expertise and their interest in a particular topic that the group works on. The working group, as with the network, will persist beyond the life of the project, and its main task is to keep up with the new developments in the field, particularly technological and metrological, and initiate and develop new requirements and documents and make them available to the end user. Another important step, and as I mentioned previously, in my opinion, one of the main steps is the establishment of a competence center for advanced blood pressure metrology at CMI, which will be able to serve the whole region. In its role as a provider, the center in Czech Republic will provide traceable calibration services for advanced simulators, while beneficiary countries will be able to develop individual strategies for the use of this joint research capacity. For instance, NMI that do not intend to continue developing their expertise in the field of blood pressure metrology will be able to outsource their work to CMI without compromising the service for their customers, and in the same freeing valuable resources and focusing on other areas of research. Furthermore, countries with NMIs or DIs that are lacking the capacity to develop and provide high-level blood pressure metrology on their own will get through this center access to high standard services provided by CMI. The center will also further expand the idea of a harmonized approach to blood pressure metrology, and will provide guidance and metrological expertise for automated manometers. As with the network and with the working group, this competence center will last beyond the project and will in the end become a part of the European Center for Medical Device Metrology. The competence center will also have the main impact in narrowing the gap between the capabilities of different European NMIs. As I mentioned already, emerging NMIs and DIs, which are lacking the capabilities or the resources to provide complete traceability chain for blood pressure measurements, will be able to serve their national customers by relying on services offered by this competence center. In addition, all knowledge gained during the project and after the project, it will be made available to everyone interested, mainly on our website, but not only. The project cooperates and will continue to cooperate with relevant standardization committees. Worth mentioning here are the technical committee 18 of the OEML, and the Joint Working Group 7 of the International Organization for Standardization. These cooperations are not only sought for guidance or in order to be in permanent contact with international stakeholders, but also with the scope of developing, revising and publishing international legal documents that would highly support our goal in the harmonization of the requirements in the field of blood pressure metrology. Moreover, due to their official status, such documents can be used when discussing with regulators and legislators potential revision of national or regional policies. Within the subcommittee 1 of the technical committee 18 of the OEML, the project partners proposed and are on their way to develop one new guideline for the evaluation of automated sphygmomanometers using oscillometric signal generators able to generate real-life oscillometric signals, and a new recommendation that sets up requirements for the evaluation of non-invasive blood pressure simulators used for the testing of automated non-invasive sphygmomanometers. While in case of the guideline, the project finds itself in the initial stage of the group forming. For the recommendation, the consortium has a draft for the first 2 parts of the intended document, and this will be posted on the page of the project by the end of October. If you are an NMI and you are interested in joining our project, please contact your national CIML representative and express your interest. It would be nice if you would be able to join as a P member, so participating member. This way you will also have the possibility to vote at the end the document. If you are not an NMI but are a metrology expert and are interested in working on these 2 documents, please either contact me or our project coordinator. The same applies to NMIs that are not OEML members. In our opinion, in particular, the new recommendation is of high interest for metrology experts, as it intends to set up requirements for all types of non-invasive blood pressure simulators, thus aiming for an international recognized harmonization of these requirements. I also included in my presentation the links to the 2 projects. So I hope you will visit us soon. And I will conclude in mentioning that through the smart specialization concept, access to high standard services in the field of blood pressure metrology will be made available to all interested European regions. In addition, the current missing harmonization of the metrological requirements at European level will be achieved, and not last precious resources will be saved. All this can and will be achieved by creating and expanding the network in the field of blood pressure metrology. This network will comprise all key participants in this field, from legislators to regulators, metrological, academic, and medical experts, as well as manufacturers in the field of blood pressure measurement. While the network is initially concentrated on blood pressure metrology, this will extend to medical device metrology in general. through their activities, both the competence center as well as the network will highly contribute to narrowing the gap between the capabilities of different regions in Europe. So I'm now at the end. If you have questions, I would be happy to answer them.
Thank you, Dana. Again, if there are any questions, if you raised your hand, I think you should be able to be unmuted. I think certainly one thing when we started this project, it did highlight very quickly the different, I suppose, regulations and the different ways that each country was monitoring and controlling these devices, and in a totally non-harmonized way, as you say. And I do think it's the way to proceed is via this network and center of excellence, so that each member state or each country does not have to duplicate effort. It's the most efficient way to proceed. So I think the smart specialization concept is one that applies not only to this area but to many areas of metrology.
Yeah, I agree. And even if several NMIs decide to build expertise in the field, I think it's important to harmonize the requirements. At the moment, there are, I think, in Europe, about 9 countries that require additional investigations in the field of blood pressure metrology for devices that are on the market. And often the requirements are very different from country to country. Some of the requirements are based on OEML documents where this exists. For simulators, they do not exist, but for automated swing manometers, they do. Others base their requirements on ISO standards. Others have individual documents, but no one thought till we started our project to come together and discuss a way to harmonize these requirements, so to make it easier for us as metrology experts, but also for manufacturers that enter the European market.
Okay. We don't have any specific question at all, so maybe it's time to perhaps open up the conversation on any of the topics that were discussed this morning, and particularly, I suppose, on the concept of smart specialization. We are one of the tasks of the project is to produce a white paper, which we have a draft stage on the area of smart specialization concept for blood pressure measurements in Europe. And again, we'd be very happy to take any comments or input from this workshop to inform that paper when we're finalizing it. So any information and any comments you would have, be it here today, or you can send it to the coordinator, Václav, or to Dana. They will be very welcome on this whole concept. So yeah, happy to open up the conversation now if anybody wishes to make any input or contribution on any of the topics covered.
Hey guys, I'm just going to allow everyone to speak. So I'm just going to do that for everyone. So if you have any questions or comments, as Paul mentioned, just please unmute your mic. Thanks.
So this is Stefan speaking. In case nobody else has a comment, I'd like to add a small comment to Gregor's presentation. If you look at the uncertainty budget for, I don't know if it was the simulator or the recording unit, you see that the pressure, the uncertainty coming from the data sheet for the pressure transducer contributes around 60%. So although Gregor mentioned that they have a very nice transducer and PDB recording unit is the same, has the same results, prices to reduce the uncertainty for the transducer go up exponentially. So this is a major contribution. Maybe an individual calibration can help to lower this number, but this I think in this particular case is maybe a good idea to reduce it. So this was a technical comment. Thank you very much.
If I may join, following your comment, Stefan, when I checked Gregor's proposal for uncertainty budget, I noticed that this large uncertainty contribution arises from long-term stability of the device. Correct me if I'm wrong, but it was something like 0.5 millimeters of mercury per 6 months or something like that. I definitely agree that this should be somehow lowered by repeated calibrations or by future investigations. So if the stability is what it seems to be, yet there are quite, if we are lucky, we might be able to reduce the stability thanks to repeated calibrations, and that would work. However, if the stability of the device would prove to be somehow discomplicated, then we would have to be produce the calibrations, the uncertainty budget as it is. So it all depends on technicalities of the device, and yeah.
Yeah, Gregor, I just have a question on the I suppose the you mentioned about commercial simulators, that they are obviously, there are commercial simulators available. But I'm assuming that none of those have produced the real life or are based on real life pulses like the one developed in this project. I suppose my question is, to establish a successful network, you know, how many of these type of real life the advanced oscillometric devices do you think we would need to have in place?
Well, we were thinking quite a lot about this, because if you use 85 signals a couple of times like Václav did, the whole test lasts for a long time. And so like, the common sense idea would be, how can I make this shorter, the whole testing? And to my knowledge, there are only a couple of commercial simulators which also have the physiologically based envelopes of these pulses, meaning they're not like directly recorded and then reproduced like this simulator is. So I don't know, up until now I haven't heard of one, but maybe I'm wrong, of a simulator which uses real life signals. But there are some which have some approximate real life signals. We do have one which has something which is like heavily based on human signals, but it's not really so. It's much nicer, like in the mathematical sense. And I think I'm sure that some really clever mathematician could calculate how many would one need to reach the same level of of reliability not to use a lot of those. But I think for the time being, I think we should stick to the ISO standard on the simulators, because there are manageable number of signals to be tested, and manageable number would be, I think, some 15 or so. And what we did, we found out that in this physiological database, there were persons having quite similar blood pressures as the suggested signals, the suggesting 15 of those. So I don't have a really clever answer, really. But what we are doing at this moment, we're trying really a normal commercial simulator, and try to repeat this if there's any difference, like huge difference between using two simulators, one with physiological signals and one with like quasi-physiological, and if there's a difference. But I don't have the data yet, so.
Okay. I see Stefan has his hand raised, so maybe he has an input on this one.
Yeah, I think he knows. Stefan,
tell us. Great, of course. Yeah, I think maybe for the start, it would be sufficient to ensure that the commercial, not so good simulator work reliable. And you can test this from time to time, following the proposals from the ISO-5. And I think since in Europe, in the European Union, the CE marking requires that the devices are clinically tested. For the beginning, you should believe in the positive result to fulfill the clinical trial, and then concentrate on the simulator, use the simulator from time to time, see how stable the device works. And as a backup, the NMI could ensure that the simulator itself is stable. So that, I think, for the beginning would be an improvement of the present situation. If you have doubts regarding the clinical results, maybe a center like CMI or at Ljubljana can use a real-life simulator to check if the clinical results can be trusted or not. So this, I think, would be a first step, and would be, I think, a huge improvement for the situation compared to now, where we only check the pressure transducer to be accurate.
Okay, thanks, Stefan.
Yeah, I agree. Maybe this is something which should be really stressed. The whole idea behind the simulators is that this is the device which actually tests the functionality of modern oscillometric electronic blood pressure monitor. Currently, the legal metrology only tests the sensor, not the brains of the monitor. When I'm explaining this to students, what's the difference between like the manual auscultatory blood pressure measuring device and the oscillometric ones? Is the oscillometric devices, they also have the nurse or the physician or the doctor already embedded in their microprocessors, and this is the problem, because we are not testing the algorithms, we are not testing the mathematics, and simulator at least tries to do this. So yeah.
Okay, has anybody anything to ask, anything to add at this stage?
Hello. Can I speak?
Yeah.
Yes, Jose.
Okay. Thank you very much. Sorry for the question, because probably some part of the questions are already answered, but I had some problems with the audio, and it's the first time I'm reading something about this interesting project. I have only 2 questions. I developed some work in the scientific and academic level about non-nutritive sucking, that for premature babies and things like that. And one problem that I had is precisely related with this project. I need to have some kind of simulator, accurate simulator, to test some devices. So the question is, you are testing here a different kind of equipment, but the simulators that were used to create the pressure, particularly the dynamic variation of pressure, were developed during this project, or they were commercially available? This is the first question, and the last one is related with the errors. One thing is to calibrate the equipment, and the other thing is to make sure that the errors caused by the positioning of the sensors are not more important than the other errors that result for the testing of the sensor and so on. So sorry if the questions are not very adequate, but I would like to have some answer. Thank you.
Okay, thank you, Jose. So I think the first question was whether the device that we've mentioned this morning, whether it was developed during the project or whether it was a commercially available one. So I think Stefan, again, you can probably answer this one.
Yes, okay. Originally the plan of this project was to look for a commercial device that could be qualified to generate the signals from the database, which we have. Unfortunately, we found out there is no commercial device available at present. And we had a fallback situation where we said, okay, we have developed such a simulator years ago, and we can use it for the project. And that was what we had to do because there was no commercial device available. And I think the situation has not changed at present. I know only this simulator in Taiwan at ITRI. There is another simulator which is let's say 95% the same, but they have modified this a little bit. And there is in Korea at KRIS, the National Metrology Institute there. There's another simulator. As far as I know, these projects are all not running at the moment. But at least there are, with KRIS, is a different approach to generate these signals. I don't know about the quality. I've read only the papers. And the second question was regarding.
I think it was the error on the position of the sensors.
Yeah. So this is one of the big advantages of the oscillometric method, because you do not need to place the sensor accurately. The whole cuff is the sensor. You need only to detect the small oscillation from the artery. That's why the positioning of the cuff is has hardly any influence on accuracy. More important is to use the right cuff. The size must be appropriate to the arm size. But there are recommendations from medical people, so I would stick with these. And so the second question, I think, is of course is is right to ask, because often positioning is a problem. In this case, I think it is of low influence.
Okay, thank you very much. Okay, thank you.
Thank you, Jose. And if you have any further questions or interest in the network, or interested in particular in the maybe the OML TC group, please feel free to contact Václav or Dana, or via the website as well, like, you know, on the actual project.
Okay, thank you. Yes, I would like very much to have some connection with this kind of research topic, because I work in the instrumentation and measurement area here in Portugal, and I think it is very interesting because it's something my wife works also in this area. This is pharmaceutical, and I like to learn a little bit more. I'm a little bit old, but I think I have still time. I hope to have time to learn a little bit more. Thank you.
Thank you. You're very welcome at the join day at the network. Okay. Have we any further input or any further questions? I think just to maybe let you know as well that that from this project, the calibration procedure, both for the simulator itself and the calibration procedure as to how you use the simulator in testing, the uncertainty budgets that is produced for using the simulator will all be an output from this project, and will be available from our website when the project finishes towards the end of this year. And as I said earlier, also there will be a white paper which will be on the whole area of smart specialization in the area of blood pressure measurements. That will also be output and available to general circulation from this project also. Any final comments, any final questions? Please raise your hand. So it doesn't appear to be the case. Therefore, I think we have come to the end of our workshop. Hopefully, you found it useful, informative, and that it's I suppose an update as to what this project has achieved, and what it will be doing, I suppose, when it finishes and when the project ends towards the end of this year. So thank you all for attending. Thank you all for your input during the course of the workshop. Particular thanks to our three speakers, Václav, Gregor, and Dana, for their presentations. And like I say, please feel free to visit the website at any stage during the course of the next few months where the project will be finishing, and where the information that I mentioned will be available. So thank you all, and enjoy the rest of the day.
Yeah. Bye. Thank you.
Bye.
Thank you, Paul. Bye.
Bye.
Thank
Bye.
you. Goodbye.
Thank you.